Lacey, Owen, showing. All right. Okay, so in the interest of time, we'll start at the top of the hour. We also have virtual audience, so therefore we should respect their time as well. Hi, everyone. My name is Julia Matevosyan. I'm Associate Director and Chief Engineer at Energy Systems Integration Group, or ESIG. And I would like to welcome you to this part of the summer workshops that we are running this week. And this specific one is on large load modeling testing and interconnection requirements. This workshop is in collaboration with National Lab of the Rockies, and it's funded by Department of Energy. And therefore, we also offer this virtual option. So I welcome virtual participants as well. All right, and maybe I'll mention right away that virtual participants are welcome to use Slido to post their questions. We will prioritize questions in the room during the sessions, but we'll also try to get to all unanswered questions after the workshop, and we'll post the responses online. So don't be shy to put your question. I'll provide just a little bit of introduction. Can you raise your hand if you're new to ESIG and never been to ESIG events before? So quite a few people. I guess it makes sense to just say a few words about who we are. We are educational nonprofit organization. We work with industry stakeholders to provide solutions to emerging questions in the energy sector. We are a relatively small organization, and so the way we provide these solutions is through convening our members and stakeholders from various sectors of the industry to get consensus on best practices, experiences that are out there, condense and distill it all, and then provide education to regulators and policymakers as they're, making their decisions. We try to stay trusted and unbiased, be practitioner-driven, working with our stakeholders. We adopt best practices from industry leaders, and we've been at it for 35 plus years. Just a few words about our membership, and I think that's the reason why we can stay unbiased is because our members introduce all sectors of energy industry. And so we have government regulators, academia, manufacturers, utilities, all system operators in North America are ESIG members. So it's 300 plus member organizations. More recently, large load representatives are also joining ESIG because we're doing large load work as well. 1,600 individuals participating in various task forces, and we have 20,000 industry participants on our mailing list. Just a word, I mentioned we do task forces, so we have this constant set of working groups, and so we divide the questions that we're working on and see under which working group it falls and spin off a task force under each. So we focus on system planning, system operation and markets, distributed energy resources, and reliability working group. This is where I spend most of my time. So anything related to integration of inverter-based resources, integration of large loads, and how they impact grid reliability. This is that working group. Just wanted to mention, because today we released one of the reports from our large load task force, which is focusing on interconnection processes. So you can check it online. This report looked into current practices with interconnection processes and studies in various regions in the US. We also looked a little bit of what's happening internationally. We try to distill best practices and make recommendations for those areas that are just trying to develop their own interconnection processes. So I'll have a few more words on this report in my presentation later today. One more thing, for the past couple of years, we've been tracking requirements for grid forming batteries, because this is also relatively new technology coming up. We wanted to kind of grow the body of work and show that technology is maturing. And so we have this webpage where we track interconnection requirements for grid forming batteries and projects with grid forming batteries. And we found it was pretty successful, and people actually use this resource quite a lot because it's one-stop shop for all requirements in the world. And so we would like to do the same for large load requirements. So interconnection requirements for large loads that are popping up everywhere. We would like to link them up on our website. If I have time, maybe we can do some kind of comparisons and make it even more useful. But check it out. If let me know if you find it useful. If you have any ideas, if we're missing any requirements, just email me at julia at esig.energy, and we'll put it there. And we'll see if this resource will be as useful as grid forming batteries one. So the next few slides are a bunch of disclaimers. So I wanted to make it short and to say just behave. All these presentations are personal opinions of presenters, so don't take any of their words out of context, don't use names and things like that. If we have any participants from regulators that are participating in active proceedings and we talk about something relevant, please feel free to leave the room during those times. Please comply with antitrust laws and avoid any conduct that unreasonably restrains competition. And we have all this non-discrimination, anti-harassment rules. So just be respectful of your colleagues. We have people of all races, genders, and ages, and we welcome just active communication and collaboration. As I mentioned, this is a part of the summer workshop series that we run this week. So I just wanted to show where this workshop fits in all of this. We had 2 workshops yesterday on integrating economic and reliability models for power system planning, and also forecasting and meteorology workshop. And today this one continues, and we are running this large load workshop the entire day. There is also networking reception this evening that welcomes all participants from all workshops, so you get an opportunity to interact not only with people in this room, but also other attendees. So just a few words about the agenda for this workshop now. We are now in the opening session, and I'll pass it on to BeiLi, who is chairing it just in a minute. So we'll have 4 presenters providing opening remarks. And then session 2 this morning is on modeling, focusing on both phasor domain and EMT models. Then we'll have lunch at noon. Session 3 is on hardware testing and model quality assessment and validation. And we'll have a break again. Session 4 is on emerging performance requirements. And so I hope I get some more references for the webpage that I just mentioned. And then 6:30 to 8, networking reception. And this is downstairs, 2nd floor, where you had breakfast this morning. All right, so shout out to our all workshop sponsors. And again, as I mentioned, we are doing it together with NLR. And so thank you all for sponsoring our workshops. And with that, I'll pass it on to BeiLi.
Thanks, Julia. My name's BeiLi, and I represent MISO. And so, as some of you may have known, MISO recently under the journey of large load initiatives in our footprint. So really happy to be here amongst the industry giant at the podium with me, as well as in the audience with me. So welcome to day 2, as Julia said, the summer session. And so thank you for your interest in participating in this discussion. And most of the folks, when we talk about large load, I think it's the first thing is we don't quite understand how the load is going to perform and what the behaviors of a load, especially when we're thinking about large load, in particular in the AI data center perspective. And so we have to take a step back to say, have we been here before? And the confidence I have in this panel and also in folks in the room is we have been here before. As Julia mentioned, we have IBR, very similar journey we started. And I think those are some of the recipe that folks have laid those bricks for us to be successful. And following that recipe book, as we don't understand some of the behavior, I think one thing is from a perspective from either regional or local, we have to think about what and why. And these are the interconnection requirements, right? What and why we care about these behaviors, either in the context of IBR or either in the context of large load. And the next thing we need to really think about is how do we demonstrate the behavior? And that's where modeling comes through. And so there's different type of modeling that's available out there. And what we have also seen as a journey unfolded for us with IBR is what we represent in a software engineering model could be different once you conduct field testing. So these are the things really weaving into the bigger discussion of large loads. And I'm so pleased to have this session that talk about how the interplay amongst the different subjects here. And so what I would also like to say is, even though we seem like we're moving very fast on the topic of large load, and we have differentiation, different kind of perspectives at the in front of you today, we do have two RTO, ERCOT, Eric, and also myself, MISO, representing our perspective. The encouraging thing, what I would also like to share is that we start converging in terms of interconnection requirements. So that's whether you look across a different RTO, ISO space, or even at a NERC, more of a federal national space, the requirement is coalescing together. So that's something else is very exciting to see. So with that, I'm going to introduce my first speaker, Murali Baggu, who is the laboratory program manager for grid interconnection. And so Murali is going to really set the foundation, a technical foundation for us to truly explain some of the challenges and also some of the opportunities associated with the large load, and some interesting work coming from the National Labs of Rocky on potential tools and potential perspectives so we can think about how do we study. So with that, I'm going to turn it over to Murali.
Thank you, BeiLi. Good morning, everyone. Nice bright morning in Denver, Colorado here. For those of you, National Laboratory of the Rockies, I just want to mention this because people have asked me this morning, formerly known as National Laboratory of Renewable Energy or National Renewable Energy Laboratory. Just want to give you a heads up. It's the same lab with a new name. We got a new name back in December, so just want to acknowledge that so that you're aware of the change here. I would like to start with thanking Department of Energy, Office of Electricity that co-sponsored this particular workshop along with ESIG, hopefully trying to disseminate some of the work that has been sponsored by Office of Electricity at Pacific Northwest National Laboratory and National Laboratory of the Rockies. I will try to set the stage. I think we have some really good presentations coming up later today, really getting into some of the details of the work that has been done in this space. But for me, I think I just really want to showcase some of the stuff that we have been doing at National Laboratory of the Rockies in the large load space, and really focus on what I call the Advanced Research in Integrated Energy Systems platform that we have worked over the past 5 to 6 years, and really show how we are using that with large loads going forward. Just, we are in a new era of increasing load growth. This has not been the case for the past 2 decades, if I'm not wrong, in the power system industry, but we are seeing that at a bigger scale. What I would say is, again, comparably speaking, right, large hyperscale data centers requires huge amount of power. I mean, it's not a new thing for anyone, but just to give a comparison, we're talking 100 to 500 megawatts, really comparable to a mid-sized town. So a new data center coming up really is talking about building new towns, middle of nowhere or close to a big pocket of loads is what we are seeing. The other thing is the load that comes from these data centers really runs 24/7. I mean, it might be intermittent, but it really runs 24/7. What I'm trying to get to is creating continuous demand curves. The reason I bring this up is you can't really replace with any other flexibility in the system or anything. We need new load. We need new generation, new conductors to really see how we can cater to this particular node. The other important thing is, people are realizing power is an important factor for data centers, but traditionally speaking, data centers really tend to look at other infrastructure like fiber optics, backbones, cheaper power, and available land. I think there is competing requirements here. It's not just a power that they are really looking after. Water is an important constraint, land is an important constraint, and other infrastructure is an important constraint. So we are competing with other important needs that data center needs going forward. I will actually dive into a few technologies that we are looking at. Again, these are more on the research side, but we have seen a lot of interest in medium voltage architectures to enable data centers connecting on the DC side of the system. Again, really looking at reliable data center integration, also solid state transformers, especially looking at converting all voltage levels to replace some of the conventional transformers, really addressing some of the supply chain needs for transformers. And a lot of analytical tools which are focused on sensors and monitoring devices to do real-time control and helping grid operators take decisions when it comes to system topology optimization and stuff like that. On the grid edge technology side, mostly this is looking at increasing the capacity of the system to host data centers. I think the first things we have seen is how can we do things like reconductoring or dynamic line rating is one of the other grid enhancing technologies we looked at. Again, traditionally power flow control devices or fax devices also allow grid operators to reroute power and really unlock available capacity and congestion in the system. Advanced conductors and reconductors, there's a lot of work that happened in this over the past one and a half year, funded by Department of Energy, really looking at how can we come up with resource adequacy needs and how can we increase those resource adequacy in the system by using things like reconductoring advanced conductors. Most recently, I'm sure there were some sessions on this, is grid farming inverters, enabling really inverter-based resources to provide stability when it comes to system black start and other needs is something that we have looked at. Again, very high level, these are some of the technologies. I'm sure we'll actually touch into some of these technologies, but I just want to get into different test beds we are working at NLR and also some of the software tools that we are working to really see how we can tackle the challenge, especially associated with large loads. You might be aware of the Advanced Research on Integrated Energy Systems, which is a DOE flexible research platform, mostly based out of the South Table Mountain campus as well as the Flatirons campus at NLR. There are two main physical assets we refer to when we say Advanced Research in Integrated Energy Systems. One is our energy system integration facility, which is more targeted towards distribution and behind the meter kind of resources, and also our Flatirons facility that you can see on the right side. Those are the two things that actually is the backbone of the hardware platform, and then the Flatirons is really targeted towards what I call substation level and a little bit on generation side of the things. We also have virtual environment, which is really a cluster of real-time digital simulations to complement what we have on the hardware side so that we can simulate bigger systems as needed along with the hardware we have. I'll just try to get into a little depth in this. Again, this is targeted to address multi-technology energy system integration challenges, including data center integration, as you'll see in some of my examples later. This is a topographical picture of our Flatirons campus. As you can see, this actually is showing specific grid assets as much as you can see. I'm not going to go through all of those, but I just want to point out a few things. There are what we call the controllable grid interfaces. I would also say these are the devices that can actually recreate grid in different configurations that we are looking for. We have two of them. One is the 7 megawatt controllable grid interface, and then the 20 megawatt controllable grid interface, left and right side, if you're really looking at the picture right there closely. And then we also have other assets like 1 megawatt energy storage systems, digital real-time simulation systems, as I mentioned, and a slew of other generation sources across the site that we can connect to if we really have to simulate different grids as we are looking at. Most recently, the control room facility is a new facility that started operations last year, really looking at connecting these devices in real-world conditions and trying to replicate systems at scale as needed. So an example of what we can do with these resources, I did point out the two controllable grid interfaces. As you can see, this is a simulation of the classical two-area system out of Kundur's textbook, if you have seen that, which is really trying to have a natural system oscillation of 0.6 hertz. That's actually on the one in the center there. But we are taking 2 points of interconnection out of that and using our controllable grid interface to simulate two different areas. The beauty of this is a two-area system. I can simulate one of them with very low reactive power and the other of them with a different condition altogether. I mean, like situations like Iberian blackout and other things. I mean, we can actually simulate that with using this two-area system and see what really happens in the power system at scale. The other thing we are trying to really see in this particular setup is actually try to see if there are natural oscillations that are seeping between the two different areas. And if there are big data centers actually that can resonate with these oscillations, how would that impact the system? That's something that we are trying to simulate and see what it looks like at a bigger scale. Again, all of this is a combination of hardware and software. The software really comes where the virtual energy emulation I mentioned about using RTDS racks and other real-time simulations, whereas the hardware is at scale hardware at 7 MVA and 20 MVA. So we can actually create bigger scale systems and really look at what that means to the system. Let me jump into data centers specifically. How can we use our controllable grid interface with that, right? Data centers, as they are evolving, are what we are seeing grid-connected microgrids or co-located generation in many cases. So again, there are two different configurations we have seen. One is the series configuration where you have the UPS connected in series with the data center into the grid. Also the parallel configuration where it actually helps with regulating the power going out into the grid. Both of those we tried simulating using our controllable grid interface. We actually also simulated the traditional side of the power system using a synchronous generator so that we can actually see the grid strength on the other side, whereas we can see the microgrid or the co-located generation on the data center side, all in hardware as I would like to. We also used our 20 megawatt and 7 megawatt simulators where 20 megawatt tried to replicate the data center load. We are trying to see how innovative we can get using the 20 megawatt grid load to simulate AI data center load, and then our 7 megawatt CGI to really replicate what I call the grid disturbances as we need. Interestingly enough, we are very close to simulating the different load profiles we have seen. We're still working on it because this is a AC to AC connection that we are talking about. We are also trying to see if we can emulate DC side of the system with DC connections as much as possible. On that note, there is a new DC emulation capability that we are building, which is a 4 megawatt capability, really looking at the DC distribution system within a multi-megawatt system. The idea is to really use solid-state transformers here to simulate the DC side of the data center and actually connect a different different solid-state transformer to replicate how a data center works. This is still evolving. I think we are anticipating this particular capability to be up and running by end of this year. But we are very excited about also looking at DC architectures with this particular capability. The other facility on our main campus is what we call energy system integration facility. I think the focus here certainly has been what I would call is the controller hardware in the loop kind of experimentation, where we are looking at the interactions with the grid, how data centers can be good citizens of the grid. So really trying to see the sequencing of how a data center can come up to full power levels, actually go down, and what does that means when it comes to interacting with the grid is what we are trying to do. I'm not going to go into this busy diagram, but this is inherently saying that we do have a system which we call the energy system integration facilities where we can connect different laboratories together to simulate systems at scale. Almost up to 2 megawatt is what we do. But again, this is where we try to do a lot of experimentation on new innovative stuff rather than up at flat irons. We really look at a production ready kind of experimentation. Example of the experimentation we have done in ESIF is a recently launched Agora large load test bed. The idea of this is to really simulate all the devices within the data center, all the way up to like circuit breakers, transformers, diesel backup generators, and also data center load, all in control hardware in the loop is what we're doing. And this is a new test bed that got opened very recently. We're looking at how brownfield data centers can help with grid integration challenges here. And as I was mentioning, really the idea of this is to understand how novel data centers really can operate using different grid conditions, and how can we really make sure the sequencing and all those are in a standard way, and really look at future standards if needed in this case. Yep. You probably might have seen this in one of the sessions yesterday. We also have a lot of capability, mostly on the software side of the things. Reopt is one of our optimization platform, mostly on grid-connected cogeneration. And then Read, Sienna, and Rev are some of our planning tools that we use to do big system simulations at NLR. I'm not going to go into deeper in these things, because I'm sure you probably have seen this in some of our other workshops, and that's not the focus primarily here. But I do want to point out one of the recent studies we have done using these tools. With that, I'll jump into some example projects. I'm sure some of the speakers later today, Shahil and Jin, might go into some of these in more detail. The first one is the one with On Energy. This is up at Flatirons, where we are using our two controllable grid interface to really connect the UPS, which is a data center AI UPS from On Energy. I think especially the 7 megawatt one, we are actually using as a grid emulator, and then the 20 megawatt one as a load or data center emulator. You can see, I think we have some exciting results coming out, but these are some of the preliminary results which I want to show, where you can see, the grid. The oscillating one there is actually the power coming out of the data center, but the green is actually the power going into the grid. So they have an UPS which has storage embedded in it that can actually produce very smooth curves into the grid, and can also take care of grid disturbances to make sure data centers don't see those disturbances. So this particular UPS is capable of doing eliminating or decoupling disturbances on both sides of the system, is one thing that we have seen. I think we have a presentation from On Energy later today, which probably will get into some of the details as we speak. Yeah. The second one, this was actually done last year. Earlier, the idea is to really see, can we create a complete data center up at Flatirons? Like complete data center campus up at Flatirons is what we are trying to do. In this particular experiment, we kind of looked at a natural gas power plant, also a storage system. We have tried with both hydrogen storage and battery energy storage, and also a data center load emulated by 20 megawatt CGI that we have. We try to demo how oscillations of data center can impact the natural gas generation, and how can we really mitigate them using energy storage system in this particular hybrid generation power plant. So just to give you a heads up and orient you, there is a video that I'm going to play in a minute here. The left side is actually the rotor of the generator. Interestingly, the rotor is rotating at 1800 RPM. So, and then the camera is at 30 frames per second. So ideally, if the rotor is just doing 1800 RPM, it should be still, because 13 times natural number is 1800. But if there are actually oscillations, you can actually see that on the system. So without any compensation for all the load, if I really just run it, you can see there is actually natural impact, right? Torsional oscillation impact on the generator right there. And again, this is just trying to see what a data center load would do to a natural generator sitting right close to in the electrical proximity. That's what we're trying to do here. The next case, we try to use both, in this particular case, we try to use our battery energy storage to really see if we can take those high frequency oscillations out using the energy storage, so that, the generator just sees the base impact of the data center load is what we're trying to do here. As you can see, in this case, it was pretty smooth, and you hardly see any movement on the shaft, just because, it is taken care by the energy storage that you're seeing there. So we are actually taking this particular experimentation to the next level. As I said, right, probably the next time we present it, we might be actually able to show you what a multi-area system might look like and how far the oscillations from data center can seep into the power system, because that's of a very high interest to many of system operators out there. Is it close by or is it way far in the system? Do I need to really worry about the oscillations that are coming in the system? What is the impact on the system shaft? How much should I worry about that? Or do we need to come up with grid codes that will actually limit these oscillations? Can we ask data center manufacturers to limit these at different levels, or something that we are trying to understand with some of these test beds? One more thing on the South Campus, as I was mentioning, right? On the Agora test bed, we did test a 70 megawatt data center using the digital real-time simulation. I think this was actually naming it, giving a name for the test bed. But it was done on our test bed using various power flow solution, especially which actually looked at combining battery and different power flow management system for medium voltage distribution out there. Didn't put any results here. There's actually at least 2 or 3 nice reports out there. This was from last year. Happy to share the reports if there is interest in it. But again, a lot of activity work going at different scales, in testing and understanding the impact of data centers, most at a supervisory level and also at the stability levels is what we're trying to look at. One thing I just want to tease up on is a recent report that we worked very closely with Office of Electricity on understanding different data and validated models to simulate every generator and transmission need out there. I think it's called one of the resource adequacy studies. Again, this is enabling the rapid identification at risk regions across the United States. We actually use the tools that I mentioned earlier for this particular study. And this is a direct product of the executive order that was released in last April, really looking at the needs for electricity demand for data centers and domestic manufacturing. Yeah. Also, we have been doing a lot of work on siting of data centers, really looking at different transmission line overlays, natural gas and power plants and data center demand. I think most recently we also looked at other infrastructure needs, and this is a preliminary map which is available online for people to look at. But anyway, there's a lot of work going on even on the siting side of the things when it comes to data center loads. I will end my presentation with this last slide. I think you'll actually see a few of these things. This is actually a direct product of the project that is funding this particular workshop. The idea here is to really come up with how can we characterize data centers both at the EMT levels and phasor model levels. I think later in this year, we are planning to really produce, publicly release some of the EMT models of the IT racks and also phasor models of the data centers. And really look at what are the issues that might arise due to, especially stability issues that might arise due to these converters that are connected to the system. I think my colleagues Shahil and Jin are going to present on some of these things in, I think, next session, if I'm not wrong. And also later in this afternoon, you'll see a lot more on the hardware validation for different models. With that, thank you very much.
Thanks, Murali. And so as Murali kind of introduced, one of the concerns we have regarding on data center is characteristic is the oscillation. And so in general, I think a lot of the industry discussion has arrived to the conclusion that data center as standalone does have introduced a lot more grid interactions, whether it's from, just Murali kind of mentioned, the oscillation it generates inherently and how it impacts the surrounding generations, especially around synchronous generations, as well as the other way around is how it quickly reacts to system disturbances and how it remains stable and online. And so with that, I would love to introduce our next speaker. Eric Meier doesn't need any introduction. He leads a team of planning, modeling, administration at ERCOT. Also, as you may have known him by his other title, which is the chair for NERC Large Load Working Group. And Eric is going to talk about some of the behavior the industry start coalescing on recognize for large load, as well as some of the national conversation and also from a regional discussion with Texas on the requirements and things that's in the works. And so with that, my honor to introduce Eric.
All right, thank you. Good morning. So, oop, let's see if I can make it through this presentation without breaking anything up here. We're going to keep this high level. We're not going to go into all the deep technical details. We'll save that later for today. But hopefully I can impress upon you the challenge that we're facing and what we need to do as some of our highest priorities and, where we're at right now. So we're just going to get right into this. So just to give you a little bit of background on ERCOT, we're the system operator for the state of Texas. We got about 85,000 megawatts of peak demand, and that's about weekend and weekday, 14 billion of transmission capacity installed. I see something popping up on my screen that says connecting, so we'll see if that goes away. But the expected capacity of 104,000 megawatts. Pause. Well, I made it about 60 seconds without breaking something, so I think that's a record. Is that a record? Woo! All right, we're back. Thank you all. So, we will not be taking questions, at least during the immediate here, but I will permit gasps of exclamation, shock, surprise. You are free to do that. So, where is ERCOT's large load queue currently at? When I pulled these numbers a little bit ago, we are a bit above 400 gigawatts. I don't know about you, 400 gigawatts is a lot to me, considering our peak demand is 85 gigawatts, and that's, equal to the size of several of the largest U.S. RTOs and ISOs. So these numbers are preliminary. ERCOT's going through its whole batch study right now. I am not going to get into that, but you can follow along and see we have a lot of demand and a lot of interest in connecting load to Texas. And now, what type of load is that? It's about all data centers, like 90% data centers. There's some unidentified stuff, which is probably data centers. So, if you are not familiar with data centers by now, hopefully you are. And if you aren't, you are getting used to that. There is some cryptocurrency and hydrogen load coming, but overall, it's a small amount. Now, we have NOAA's Large Load Task Force that is studying all large loads, but it is computational loads that are posing the biggest risk to the system today. So, this was touched on a little bit. What is changing? We had distributed loads across residential, commercial, industrial users. To those of you that don't recognize, that is Edison's Pearl Street Station. So, in the last 140 years, maybe 30, since we first brought power stations onto the grid, we are looking to more than double 150 years worth of power demand in the next decade if these projections materialize. That is a huge challenge. That is going to be a huge risk. We say it's like IBRs, and it is, but even IBRs didn't move that fast. So we have to keep that in mind, and you need to all be working to assure the reliability of the power system. And where is the future? We have single site loads that rival regional demands. I think, the largest I've seen is up to 6 to 11 gigawatts for a single site. That is gigantic. And now we have power electronic based loads and interfaces with solid state transformers and stuff like that. So I'm not going to repeat everything on these slides. It's about to come up, but I'll give you some of the key points. We have more demand at a single site than any load that is connected to the grid ever before. We have power electronic based loads that were previously motor driven and have extremely fast response times, and they're software controlled. So just like IBRs, you can update these on the fly. And now you have to ask the question, is my load model correct? Or did somebody change something in the field? Good luck figuring that out. You're going to have to. So the disconnection of data centers obviously can pose risk to the grid, see high frequencies, high voltage, trigger protection, and lead to potential cascading outages. If you're from a utility and you're not studying data center interconnections on your system right now from a reliability impact, you should be. And you need to respond to NERC level 3 alert, and you need to going to have to explain, no, I don't have a study, and here's why. So standards are coming. We are targeting approval by the end of the year for Project 2026-02 for the NERC board, and then it'll go to FERC. So just keep that in mind. I do like this by Epoch AI. I filtered out everything that was not gigawatt scale in its end use. And we're still left with like 15, 20 facilities by 2029. Now, I don't know if all of these are in the United States, so take a word of caution. But that is just a lot of gigawatt scale facilities that they are tracking. And there's many, many more that are sub gigawatt scale, but are hundreds and hundreds of megawatts. Reality is changing. You need to change with it. We all do. So I won't go into all the details on the NERC's white papers. I recommend you read them from the Large Load Working Group. But really, we found that, large computational loads are posing risk to the grid. They're posing risk today, as documented by NERC's incident reports for Virginia and Texas. There's been demand reduction and events in Ireland, American Electric Power, and other regions across the world. This is not theoretical. The risk is here today, and it is up to us to address it. So, you can have ride-through issues, disturbances, oscillations, protection and control systems that I said do not respond as expected, but they did respond as expected. It's just nobody anticipated that. And when everything behaves as expected, but the grid still fails, we have a problem. And then we also have rapid ramps that can pose challenges, and then large computational loads can be built faster than load and generation. So what do we need? Uniform performance requirements. We need, which includes post-fault active power recovery, FRT, VRT, oscillation management, and then the ability to properly model these loads. Because if we don't have that, we're flying blind. We can't study anything. So within disturbance performance, the disconnection, high frequency, high voltage, and really VRT, FRT, and PFA, PR. Now, there's other metrics of disturbance performance. I quote these three as these are what we're focusing on first within NERC's Large Load Working Group. And then most power electronics today is designed to the ITIC curve. Hopefully y'all are familiar with the ITIC curve. If you're not, go read on it, also called the ITI curve or CBEMA. And this is really just defining the regions where power supplies and similar types of equipment will stay connected and operate normally, or will they will protect themselves. Some other considerations are protection systems. So you want to make sure that your protection systems are coordinated. What we've seen in many regions is that they are looking at the number of disturbances, counting that, and if it's too high, oops, I'm going to backup power. And that is a normal operation mode for these facilities. Number one goal, they want to make money. So they're going to do what they can to stay connected and keep power in their facility and switch to backup power to make money. But that doesn't do well for the grid if you don't plan for it. And you have dozens of facilities acting in concert and suddenly tripping out. So that's something to think about. It likely originated from the distribution side. A lot of these data centers, right? 10 megawatts, 20 megawatts distribution connected. This is a bit more of a normal practice there, but it doesn't really work on the transmission grid. So you need to consider, what are your high speed reclosing times, and then make sure that you account for those clearing times also in your event detection timers, and then within your, control schemes for the load. So you want to make sure that you're not prematurely tripping, but you also don't want to wait too long to trip your facility because then you're going to have problems. So I can't claim ownership of this or originate. We can really thank Dominion for quite a bit of the work that they've done in this area. But I really wanted to highlight, this is one of those key things. It's not a discrete performance requirement is imposed on the load itself, but it is something that is, you really need to consider, and you need to make sure that this is set appropriately for the load to work. And this is not the utility, this is the load that needs to do this. We see oscillation risk. So this one is from ERCOT, but we've seen across also oscillations in Dominion. So these loads, the repetitive demand can cause forced oscillation, and also you can have resonant and converter-driven instabilities with their power electronic interface. Basically, every one that I've seen so far, including others that are out there, it's mostly been traced back to the power supplies and the uninterruptible power supply units, and that's where a lot of the controls need to be modified in order to damp the oscillation and remove it. So the tricky part there is you have to keep up with the controls, and you have to continuously review them, make sure they're working, because if you change the load profile, you change the technology at the back end of the data center, all of a sudden what was once true may no longer be true. And these facilities will be replacing hardware every few years. They're constantly upgrading equipment in there. And so just keep that in mind as you write your definition of a qualified change to your facility. Now, we've seen them in North America. We've seen them in ERCOT. We have seen subsynchronous oscillation. One of the things I'll leave you with is originally, PMU measurements were not always enough to detect it. You did need good DFR data and high quality measurements. There's a great report that just came out from PNNL on, PMU adequacy for large data centers. So I'd recommend you all look at that. Data center modeling is another big area. Events have shown that we cannot replicate events with good data center models. You need a power electronic interface. You need good load profiles. You need to behavior response controls. And not all data centers are the same, right? So certain facilities may not have UPSs. And then the availability of information is huge. So if you are an OEM, please, we need you to work with us. We need you to help us figure out what's going on and to build good models of your equipment. Now, we're going to get into the changing data center in a few moments. So there's some questions on how we need to do that in the future, but you also need a process for, capturing ongoing changes to these models. And, like IBRs can be updated on the fly with software, you can do the same for these loads. I can change some code, deploy it out, and I've just changed the load profile. Does my model account for that? Does my system account for that? That's something you really gotta figure out. And then once you have the models, of course, event verification, and just make sure that your models perform as expected given that event. So we're going to talk just a little bit about the evolving data center, and then we'll wrap it up. One of my other passion projects is to participate in the Open Compute project. So if you don't know what that is, it's a group in the IT industry where they really come up with new server designs, power infrastructure, and so forth for the next generation of data centers, and sort of, that will be adopted by OEMs, hyperscalers, and so forth. So one of the things that's going on is, as racks are pushing to a megawatt with AI workloads, you can't use the current data center architecture. You can, but it's just not as efficient cost and space-wise and energy-wise. So they're really looking at low voltage direct current distribution in a data center. So that's looking at an 800 volt architecture from NVIDIA, and the Open Compute projects Mount Diablo 400 volts. It's probably going to end up with 800 volts. There's a white paper that was released earlier this year on the LVDC specifications. But I say this so you all keep in mind, the models you build today are probably not going to be the models you need tomorrow as the hardware continues to change and as the designs continue to change. So we can't this is not a one and done problem. This is something that we need to continuously monitor and make sure that systems perform as expected. So I did make a graph over here a while ago for one of the OCP papers, and this is showing the ERCOT right-through curve over the ITIC curve, and then the UPS voltage curve, and that's from a DOE Energy Star. It's like an open standard, and that's what they pointed me to. So we can see that there's a performance gap. The gap between the red and the green, the red and the green between the blue. We got to, make that performance up so that way your facility can meet these requirements, or it may not be allowed to connect to the grid. So that's something that's, as you just mentioned, the on-energy UPS, there's all sorts of other systems that are in design and testing that work is needed to make that up. And it's not just as simple as flipping a switch, and the current facility can do it. So one of the other things I'll call out is solid-state transformers. So solid-state transformers are emerging where they really want to use an SST to power that low-voltage distribution system. And you can also couple with battery storage, help you meet some requirements. But one of the warnings, cautions I'll give you all is we've seen issues with IBRs. They're power electronic software-based. Is the same thing with SSTs. We're introducing a new controllable power electronic interface, and we need to make sure that models are accurate and that we have continuous updates, continuous monitoring of the control parameters, and so forth. So just something to think about. We're introducing a new power electronic interface, and that's a challenge. So what's the implication for the grid? You need to coordinate your protection and control. Right now, we're generally talking down to the UPS and PSU level. Hopefully, we can abstract that away more with SSTs and other technologies. The deeper we have to go into data center, the more complicated it is for everyone. And then, larger facilities with co-location, you really got to coordinate these things or you may damage generation. We need to upgrade grid codes. We need to study this, and we need to look at our protection and control behavior. Now, one thing I'll tell you is, if we come up with requirements tomorrow, it's going to be at least 2+ years till the hardware can be designed against that and make its way into the next generation of data centers. So the longer we wait, the longer we risk excavating these problems. And it's something to think about. We need to move fast. We need to move with urgency. We also need to recognize that we have a limited amount of time and resources. So we have to pick our problems carefully. So just something to think about. Now, I am going to briefly, in my last 2 slides, number one, look at the reliability guideline. So NERC published the risk mitigations for emerging large loads reliability guideline in April. Raise your hand if you have read it. Uh-oh. Raise your hand if you're with the utility. Okay, there's only 2 hands up. I thought that would be more. But if you are a utility, and generally if you're a NERC registered entity or you're a data center owner operator, you should read this because these are coming for you. We are moving forward with standards to implement some of these things and these requirements, not all at once, but time is ticking. The clock is ticking. So review it, implement the recommendations, and then hopefully you will be doing your part to help safeguard BPS reliability. I don't think any of us wants to be here in a year or 2 and be discussing the results of some sort of blackout because we had known the problem, but nobody did anything. I urge you to look at this, to take it seriously. The risk to the system is real. We've had this demonstrated across events in Europe and North America. And at this rate, we are in a race against time to get the appropriate mitigations in place before something worse happens. So please work on this. Now, we can't do it alone. So raise your hand if you are experienced in utility, transmission planning, operations, and so forth. Now, keep your hand up. Keep your hands up. Keep your hands up if you are also well-versed in power electronics. Oh boy. So I think there's one hand back there. Maybe there's two. And, we are dealing with the interaction between power electronics, where we have to have a better understanding of these facilities. I mean, same with IBRs. And so, we can't do this alone. We're not experts in power electronics. We need to work with our partners at the national labs, with universities, and across the industry. We also really need to engage with data center developers, equipment manufacturers, and so forth. So I will lead by saying, new standards are on the way. I've mentioned 2026 or two. So we have CLE 1, CLE 2, and CLE 3, which are being drafted. Those drafting team meetings are public, and the first round of those standards going out for review will be in August, but anybody's free to join. We've also, last week, we had IEEE 4200 approved to begin standards development, which is performance requirements for data centers. And that'll be a global IEEE standard. We'll be following up with conformity assessment and device interoperability and so forth. So please get involved. We can't do this by ourselves. Thank you. Questions and comments we'll save till the end.
Right. Thanks, Eric. And I'm going to pick up where Eric left off by we cannot do it alone. I think from the previous presentations and also your own expertise, you can see from a macro perspective, there is a interaction with the system. But as also Eric kind of pointed out, in the detail micro level, the different setting, how you can potentially have these implications as well. So it's my pleasure to introduce my good friend, Julia Metavosian. And so I think I said last name correctly. And so associate director, as well as the chief engineer, a title that many people envy here at ESIG. And so I want to also just tee up her topic across the industry. As Eric kind of pointed out, we have different type of regional concerns and also coalesce at a national level. And when we think about the solution, especially with the large load or data center, there's really two different kind of solution space. One is what can we do from an equipment perspective, and that's upgrading the UPS. So we have also seen advancements, although not fast enough from a UPS perspective. But we also have seen how the system can come together as a solution as well. So with that, I want to introduce Julia's topic and updating on the large load effort here at ESIG and bring together all the different perspectives. So with that, please join me in welcoming Julia.
Thank you, BeiLi. All right. Let me continue. So yeah, so you've seen on one of the last slides from Eric, if you haven't spun off the large load task force, you're behind. So we have one. We started in December 2024, and we are currently wrapping up last reports from the task force. I'll skip the slides on ESIG because I talked about it in the opening. So just to show you how ESIG task force looks like, not all of the topics that we addressed are related to the workshop today, but I wanted to show you the whole thing. So we spun off this large load task force, recognizing that it's a very multifaceted question on large load integration. So we had this 7 work streams looking at what are the data needs for large loads, large load forecasting, interconnection performance requirements, modeling requirements, transmission planning with large loads, resource adequacy assessments as large loads are integrating into the grid. What are market participation models and what are some of the operational considerations. There is a QR code that if you scan it will take you to the large load task force page, and there is where we post reports as they come out. If you're ESIG member, you can log in and also get to materials that were shared during large load task force convenings, some presentation materials and things like that. I think just kind of to set the scene, maybe one more thing before I change the slide. For this workshop today, I think the relevant topics from large load task force our interconnection performance requirements, so we'll talk about it in the last session today, modeling requirements, so we'll talk about both modeling needs, but also needs on model validation and how do you test and validate those models as they are being developed. One thing we are probably not covering in this workshop today is interconnection process and interconnection studies, but I think that's also very much related to the topics of the workshop because both requirements and models feed into interconnection studies, and studies are part of the interconnection process. So maybe not to repeat some of the things that Eric said, this is something I'll focus more in my presentation here. So Eric talked about reliability concerns with large loads more from the system operator perspective. As I mentioned, in ESIG, we are trying to get everybody at the table and solve the problems kind of at the equal ground. And so I maybe focus more on challenges for large load developers. And so I'll go through the challenges, and Eric mentioned grid operator concerns, and I'll also mention what are the challenges for the data center developer. So this large single contingency size is the concern for the system as a whole, a system-wide concern. As a large load developer, you maybe don't really understand what's the importance of this because you are so just focused on your own project. But what it can result in are operational restrictions because, for example, system cannot handle a single contingency of disconnecting just one large load site. And there may be phased energization restrictions, so you cannot energize the whole project right away, but you need to do it in stages. So these are concerns that developer has to be aware of, but this is also a moving target because I think as system operators are developing some of the mitigation measures, maybe initially it's some kind of curtailments or restrictions. Later on, maybe there is some kind of right-through requirements that actually reduce the amount of single contingency that we can face. This single largest contingency that we have, it will keep changing. One other thing that may be introduced are some kind of reserves to counteract large load loss, and that may help in the future. But again, in the meantime, there may be more restrictions on large loads. Eric mentioned power electronic interface, so all of the impacts that are coming from that. What that results in and how it impacts the data center developer is that they now need to procure this phasor domain and EMT models to provide to system operators for all the interconnection studies, and that may raise some IP concerns with the manufacturers. Modeling limitations, so existing models that we use for large loads historically, they are not sufficient, and you'll hear much more about it during the course of the workshop today. The models from the system perspective need to accurately represent large load behavior for many different scenarios and grid conditions. So developers may need to coordinate with OEMs to get these models. And again, I think it's more challenging than for inverter-based resources previously because you probably deal with multiple manufacturers and vendors, and the design of the large load data centers may be more diverse than what you see in IBRs today. Need for EMT studies, so a lot of this phenomena that Eric mentioned require more detailed EMT studies, and this is something that have not been traditionally done to look at large loads, maybe just, in industrial large load design somewhere, it was done before, but not on a system level. So there is a need for aggregated yet detailed EMT models. Voltage stability, so dynamic voltage behavior of large loads during faults may require additional reactive power compensation equipment that maybe data center developer haven't actually planned on installing from the beginning. Co-located generation, this is a question that it's kind of like if you look at how we are working through these issues, it comes kind of as a secondary, but I think we need to think about it more and more holistically. How do we study co-located generation, co-located batteries with large loads? What scenarios we plan for? from one hand, we have this interconnection requirements for large loads. Maybe it incentivizes a large load, put a battery with the site, but then the way we study them in the interconnection studies may kind of take away this advantage of compensating for interconnection requirements, and now you also have a resource and additional restrictions on your site. Reliability standards, Eric mentioned, everybody's working on it, and those are being developed, being put out. System operators are thinking kind of from system perspective how to protect the system. I think large load developers are coming together to understand there will be this reliability requirements, but the challenge for them, I think, is that it's ever moving target. There is no standard requirement. So, and you can have, you can be in the process of developing a project, and requirements are changing as you go. So it's very challenging. I think it would be better if there was a requirement already before the project is, being designed, or some kind of like grandfathering rules are adopted. And then post-commissioning compliance. So that's something that came in very late for inverter-based resources. And I think we need to think about, we need to learn that lesson from IBRs, and we need to think about it sooner as we're integrating large loads. So as Eric said, it's not done once and that's it. You will need to monitor what's happening. You need to update models on an ongoing basis. So I mentioned this interconnection process report that just came out. And again, because this is not the main focus of the workshop, but is very relevant to everything we'll be talking about, I'll focus on this just a little bit more. We looked at interconnection process and study requirements that are already out there in North America. So looked at system operators, utilities that already have some kind of interconnection process for large loads, if you will. So we found this phases that, if you look at it, reminds you quite a lot of IBR interconnection process, and I think that's not a surprise. I heard from one system operator's interconnection person saying, "Oh, I don't want to do this for large loads. It's already, the process is already broken for IBRs," and I don't think we have a choice. I think we will have to do it in a similar way as we do for IBRs. Things that don't work for IBRs will not work for large loads either, but we have to figure out both of these issues as we go and kind of learn lessons from both of the processes. So several milestones that are here, pre-application phase, interconnection application, some kind of screening study to understand if this project even makes sense in the area where it wants to connect. System impact studies, so kind of similar to what we do for IBRs today. Large load facility study, interconnection agreement then is signed, and then construction and commissioning is happening. Some things need to be done there. And then, as I mentioned, this is not a part of interconnection process, but very important step is post-commissioning monitoring and compliance. And so just some of the recommendations that came out of the interconnection process report is that in this initial stage of milestone 1, where you do pre-application phase, define milestone requirements and process steps. So as a large load developers go into the process, they actually know what kind of information is required, what kind of models will be required during the process, what are their readiness requirements along the way, and all those things. Hosting capacity is maybe something, or some sort of indication of where there is space on the grid to connect large loads. That would be extremely helpful for developers and to maybe reduce number of applications in the queue, so it's not 400 gigawatts for 85 gigawatt system. Then as you go into interconnection application stage, define data intake requirements. So, for the system operator to sit down and think through what are the data that I will need, and maybe again, lessons learned from IBRs. Coordination and information sharing between utilities, ISOs, RTOs is very important, so that same information is being used across the board for impact studies later on in the process. And then readiness requirements, again, carefully thinking of how you identify if these projects are real or not. It will help to reduce duplication of work. The milestone 3 is like as we are going into screening studies, improve queue transparency and harmonized treatment of duplicated projects. So if you identify the projects are duplicates, think about how you're going to study them so that the work can be reduced and the time it takes for actual real projects to process is less. As you go into interconnection studies, define what studies will be done so that when developer goes in, they actually know what it takes, what are the modeling requirements, what are performance requirements, and all of this will inform data center design. We are talking about cluster study approaches now and implementing it for IBRs. It definitely makes a lot of sense for large loads as well. But also, I think, and maybe we haven't highlighted it enough in the report, but combining all of this into single integrated study, and that's something we talked about yesterday, makes a lot of sense. Like it doesn't make sense to study cluster of generators separately, cluster of loads separately, coming up with different transmission projects for either one of them. It makes sense to study them all together and see what our overall transmission needs for the entire system, and that may come out with a more optimal and efficient plan. Define financial commitment and withdrawal penalties. So that's during as the large load facility studies are starting, there needs to be some financial commitment from projects that are likely to go ahead, and withdrawal penalties so that there is less incentive for unviable projects to stay in the queue for too long. When interconnection agreement is signed, and I think Eric talked about it, it's very important to develop a process for material modification. So as large load data center design is changing, how models are updated, what studies need to be repeated, when is it happening during interconnection process. So these steps need to be thought about and worked out. And so the last one is define commissioning testing, and also what kind of model validation can be done at this stage based on commissioning tests, and how do we true up what have been modeled and studied with what actually have been built to ensure that at least at the end of the interconnection process, the models that we have now in all the planning models and operational models are reflecting to what have been installed. And then for the post-commissioning, for the lifetime of the project, what are the requirements for ongoing model validation, conformity assessments with applicable interconnection requirements, and monitoring requirements. I'm doing, just have 5 minutes. So I'll just zoom through this too, because we'll be talking much more about this in session 2 and also in the last session. So as I mentioned, we already have published the report on performance requirements. I really like the way we approached it. So instead of recommending specific settings for performance requirements, the report actually looks at what are the system operators' considerations that go into these performance requirements. And maybe it helps data center developers to understand kind of where the system operators are coming from and why certain numbers are being proposed. So as a report, going through all of these requirements for normal operation, for disturbance conditions, for protection coordination, modeling requirements, and operational requirements, it talks about what are the system operators' concerns and how that manifests itself in requirements, how requirements are likely to look like. Large load modeling and dynamic studies, you'll hear from Parag Mitra from EPRI, who actually led this effort for ESIG. This report talks a little bit, first provides just a background of how large load models, been developed over time traditionally, and where it breaks for new large loads that are power electronic based. It looks at what models should capture for this new power electronic large loads, and looking at all these different phenomena that we would like models to capture, and therefore people need to work with manufacturers and get models of these pieces of the data center. And then it provides modeling recommendations on standardized modeling requirements, both for phase and domain and EMT models. It talks about usefulness of generic and user-defined models, And I think, again, a lot of lessons learned from IBRs here, while we all want to have, as standardized and as generic models as it's possible. Still, each data center will be unique, and for interconnection level studies, it's the best to use user-defined models that is based on actual equipment and actual plant design. But it's probably impractical for planning studies, for early stage interconnection screening type of studies, and so generic models will have the place and will be needed. Model quality testing, so model itself is not enough. We've seen a lot of issues with that with IBRs, where model is provided but it's not representative of a plant and therefore is not very useful. So you need to do model quality tests to make sure the model is actually usable, but also model validation to make sure that it represents the plans, and then talks about industry collaboration and integration. You'll hear much more details about this, two of the three reports, and I encourage you to have a look at those. And here's my email. If we missed any requirements of the webpage, please let me know. With that, save us a little bit of time. Thank you.
Thanks, Julia. I think one of the things Julia also pointed out from her presentation is coming from an RTO ISO perspective, we're very much so focused on reliability. But also I appreciate she's also teeing up just there are some practical challenges, in particular from a modeling perspective for the developers. So with that, round out this discussion, we do have a pleasure of having Meier, who is the Power and Grid Strategy Director at Diode Venture, talking about what are some of the challenges from the developer's perspective. And so with that, thank you, Meier.
All right, good morning, everyone. So yeah, I'm Murali Sayed. I work at Diode Ventures, and those were some great presentations earlier. I am from Eric's favorite industry, data center developers. So moving into, I'll just give a quick overview of who we are. We are a wholly owned subsidiary of Black & Veatch. We de-risk sites for land, power, and water, going through site selection, community engagements, and get it to a point where it's ready for a hyperscale tenant to take over. Our focus has been on grid strategy quite a bit. My background is in transmission planning, so we are in several markets all across the US, and we work closely with the TSPs and the coordinate and other stakeholders to coordinate our interconnection applications, go in as good grid citizens, and try to be partners in our development. So we also take part in regulatory landscape, be involved in NERC, ESIG, and ISO large load work streams. We also rely on our EPC background quite a bit, so come up with standardized designs early on during preliminary stage, where even though we may not have the most up-to-date information around what actually goes into the data center eventually, we are starting from a baseline that's actually based on our experience. So I wanted to kind of also talk about what are the different stakeholders that we work with. So we pretty much predominantly three parties, right? The end customer, the hyperscale tenant, they have their own priorities and timelines. Historically, they have been, it's all about how much power I can get and when I can get it. The quick energization, future scalability, but that's now changing. While in the past they didn't think about grid reliability as much, but now things are changing there. So working with OEMs is also very important, better as other presenters have covered, better understand what how they operate, get their data sheets, and still try to, even though they have a lot of proprietary information, try to figure out exactly how we can continue to provide more reliable models in the future, and also work closely with the TSPs, understand their processes and the requirements, and responsibility from a model development standpoint would be very similar things that Julia covered earlier. Get good model quality, submit it, then keep that model current based on any design changes that happen throughout the process. Coordinate with the OEM, validate where you can do some validation or verification of the parameters, and also continue to have these stakeholder alignments across throughout the application stage and the process in general. Now, so I'll talk about a little bit about the interconnection process. I mean, this is about modeling, but I wanted to at least draw parallels around what happens when we are doing so there's this interconnection application. This is largely similar, different ways industry is doing studies, but predominantly how the application process goes and what's going on behind the scenes on the developer side. So early on, we understand we want to be in a market. We know that system. We do our due diligence, go through the IRP, understand, get the CI data, understand generation pockets, load pockets, constraints, and go in as a partner, better understand the reliability concerns in the region, and then have those early conversations with the utilities, do those pre-application discussions. If we are satisfied that this is somewhere you can actually successfully develop a data center project, we start doing some identification of sites, due diligence around there, and by the time you submit the application, you secure some land control, start providing data collection items, any other modeling requirements that are needed, get those engineering studies kicked off, and behind the scenes, you develop your preliminary design, then submit any modeling packages, but at the same time start doing those desktop studies, community engagement. And as the studies are getting finalized, you get into those planning and zoning efforts. And the idea is there are several work streams going on, right? You are working on power, land, water, fiber, whatnot, right? And you want to make sure that all of these work streams converge when you have to make some major decisions. These days, when you have an electric service agreement in hand and utilities have done their process and studies, you have only so much time before you have to commit, right? Otherwise, you're back in the line and others can commit. So the delays in one process can delay the other process, and that's why it's very much important to understand exactly what they have clarity on the interconnection process from the utilities so that we can plan accordingly. And so I want to take some time to also talk about the different types of developers that are out there and taking part in the interconnection process. Not every developer is the same. You have powered land developers that are developing powered land for end users. There, the design control is different, right? You have more understanding of, okay, the preliminary design, what's going into the study, and what's being what you have to do until the, let's say, the ESA stage, right? But when it comes to commissioning and operate, not much information is available at the time. So that's why some of the modeling standards and working with UPS manufacturers and other OEMs to better get some early stage models that are rooted in some of the industry data are important. Powered shell developers, these guys are the ones who will build the buildings, so get into the constructions. They also get long lead items, so they have more clarity around the build and commissioning stage. But then again, they will also may not have information on the exact AI load profile and any other information you may need from a operation standpoint. But then there's hyperscale operators, right? They own the design, build, and operations, so they can have full visibility across the board. But you have to understand a project isn't real until you at least have an answer and a commitment from the utility when it comes to how much power I can get, when I can get it, how I can scale my system, and some of the other work streams I talked about. So a lot of times, some of the design decisions haven't been made. There are several OEMs they work with, which one's going to actually go into that specific data center, what kind of AI load profile, or is it cloud data center? The load profile is not known either for them as well. So while they may be able to provide some historical data, the specific details around the specific project may come later. And some of the interconnection challenges I mentioned earlier, right? This kind of covers the interconnection part of things where you own the interconnection as a powered land developer, but the process, but when it comes to tenant and equipment selection, you may not be able to commit to something specific. So from a modeling standpoint, while you can build those models on standardized designs, you don't have as-built information. Powered shell developers, they might be able to provide some more information around long lead items and may have some other tie-ups or tenants identified already, then they may be able to provide a little bit more info. but a lot of times they might see the same kind of bottlenecks that the land developers, power land developers see. Hyperscalers, they have strong utility relationships, but then again, but then the interconnection timelines are limited by capacity constraints and long lead item timelines. So there's only so much they can get out of it. While they are starting to have some in-house modeling teams that understand what's needed on the grid side, as I mentioned earlier, they may not be able to get the information you need for that specific data center until the design teams are engaged and some of the decisions have been made. But like everybody said, even after operations have started, things can change. Now, getting into the regulatory landscape, it's important for developers to be aware of this. As discussed earlier, we went from alerts to standards pretty quick. This is evolving rapidly. And what we are seeing on the system, as mentioned earlier by other presenters here, there's sudden load reductions, oscillations, those things are impacting the operation of the grid, and there are legitimate concerns around those. And with the summer peak demand and growing significantly over the next 10 years, especially predominantly because of data centers, so computational loads, we are seeing this urgency from a regulatory standpoint to move fast, right? So NERC Level 3 alert that was mentioned earlier came out with 7 essential actions, asking utilities and other stakeholders to provide information and gather information and report to NERC in August. So predominantly, so I've put this out there to understand different things that are being captured. But ultimately, it all comes down to how these actions relate to the disturbance performance, right? So a fault happens, you have voltage or frequency excursions. In the past, a lot of these larger loads were able to handle these or stay connected on the grid. But for data centers, primary driver is to keep their equipment safe, continue to operate. They have on-site generation, they have backup generation. So the tendency in the past used to be just back off, right, if something happens. But now that's changing, where we have to be good grid citizens, so better understand the reliability needs of the grid. And so that's why you got to work with the UPS manufacturers and other OEMs to figure out how to meet some of these requirements. Now, so I try to capture some of the things that you got to do from a modeling standpoint, right? You characterize the load, try to understand as much as possible how the load would operate and capture that behavior in your models. Work with OEMs and stay connected with them to continue to tune and provide spec for those equipment. And in the future, once commissioning is done, you continue to do recording, on-site recording, and whatever you need to do to continue to keep those models up to date. Now, from a challenges standpoint, I've touched these a little bit, so I'm going to keep it high level. There are some great presentations coming during the rest of the day. Parag, with as it was mentioned about the ESIG report that is there for the dynamic modeling, that's a good. There's some good information in there, but this is just high level, right? You have different types of models: PSSE, PSCAD based, RMS, and EMT modeling, addressing different things. Have their own strengths and challenges that you got to watch out for. And so we as an industry are trying to figure out exactly when we do the EMT studies, when we need the PSSE models, how much you need to model, how much you need to study before you commit to a data center. Interconnection processes getting defined based on those data points are very important. So what are the 3 activities that make the large load model trustworthy, right? This is very similar to what we went through in the IBR industry generation side, right? You don't want to do verification, have the as-built models, matching your specific parameters one-to-one, have where you cannot match or don't have the ability to look into the OEM data. You get those attestations in place to be able to get those attestations from the OEMs that the model behaves as one would expect on site. Then there's validation, right? You measure, you compare your simulated models to your measurements on site under disturbance behaviors, or if there's some event happens, you should be able to, you should be capturing with enough fidelity that you can compare in the future with the models and update the models as needed. Then model quality testing, this has been done quite a bit on the generation side, and we are starting to see similar requirements on the large load side. Those your regular voltage step up, step downs, frequency changes, right through settings and phase shift. So you start testing testing all of those for each model. Now, challenges, as I mentioned earlier, right? Greenfield, you don't have any field data. It's pre-energization, while there might be some factory tests for converters specifically. For the complete site itself, you don't have a validated model. So while you can do benchmarking against each PSSE or EMT and RMS models, benchmarking against on-site data is not possible early on, and hardware in the loop, that provides some good value, but probably provides more value when you have actual as-built designs and OEMs are confirmed. So validation, you have those test bench, you reproduce benchmark events with enough fidelity. You do the comparisons, you do version control on those models. So as the firmware changes and design changes, hopefully there are processes in place. Sorry, gotta have some water, but processes in place to be able to do the comparison there. So post energization, as mentioned earlier, have high resolution recordings, be able to compare, periodic review. So utilities will come up with their own processes on when you should compare compare information. So yes, utilities will start to have their own processes on when there will be periodic reviews, mandated modeling updates based on qualified changes, and then the benchmarking of the models themselves. Solutions, right? As we know, hardware in the loop, that's coming up. There are some great test benches out there. There'll be some great presentations later in the day talking about this, but I just wanted to give a high-level overview, and then people will go into much deeper into these. But you can use real controller hardware, you can use real-time simulated grids and start evaluating the load behavior before the construction. You have those control and protection validation done before you actually implement things on site. You can start doing some interaction, observe those any potential interactions early on. There are, based on our designs, I mean, a lot of times battery energy storage is on site, some on-site generation, and then obviously with inverter-based resources, you can start looking into how those will work with the data center side as well. And so these test benches and simulators, they are the most practical way to learn about how a facility would behave before it's energized. And yeah, I'll encourage to sit through some of those presentations later. So how do developers build those credibility, right? And as you start getting required compliance, how do you meet those, right? You have those, you rely on those HIL test beds, start verifying your requirements, verifying your settings against your field information. You start doing site simulations, benchmarking to represent on-site equipment performance under different conditions. On the commissioning side, you do on-site testing, and then there are processes that are coming up which will be very helpful for data center developers as well. And you do the measurements, you study, then you address, right? You measure what's happening on the grid. You see if your models were responding the same way as what you saw on the grid, and if there were differences, then you address them. You work with OEMs or whatever you need to do to address those shortcomings in the models, and continue to update those models through, and then have a way to be able to verify that those models were updated when changes were made. So with everything, I'll leave you with this. I want to reframe this modeling conversation. First thing, if the idea is the developer knows everything and we need that information, I mentioned earlier, different types of developers, different kind of information available, the projects aren't defined yet, they're not real. I mean, yes, you want to find out whether a project is real. The idea is we want to build those projects, but until we have some answers around what can be done, there's no much design information, right? So let's define what's known and when it is known, and work through figuring out which studies are absolute, which studies we need to do, how much commitment we can provide, and then have your interconnection process set up in a way where you have the ability to do more studies. So, I know if the idea is I know what to expect from data centers because I did the studies up front. That's not really true because, again, the data center design, load profile, and characteristics will change. So your processes need to reflect that. And even if you're asking for exact values before design decisions are made, we'll do everything to provide the best available information. But then the idea would be to have more clarity on the interconnection process itself, to better understand what will be constituted as material modification or qualified change. And if it's well defined and the processes are well in place, then you can do re-studies on the dynamic behavior, because there's still time when after signing some things to actually energizing the asset, there are ways to be able to address anything else that's identified based on the actual design. Then lastly, this would be for the developers, right? If we are saying, I will wait for the utility industry to tell me what the needs are from a process updates and standards standpoint, that's not going to work as well. So you want to get involved early in the process and standards development, review those draft proposals, and actively engage in learning the grid reliability concerns, because standards that are written without developer input still apply to developers, right? So you might as well be involved in the conversation. That's it. Thank you.